So, hello and welcome to the first episode of The Science of. In this episode, we are going to talk about the warp drive. Since you clicked on this video, I presume you know what a warp drive is, but for those who don't, a warp drive is basically an engine which enables a starship to go faster than the speed of light. It was first used in the popular science fiction franchise Star Trek, and is today basically a household name in the world of science fiction. But how exactly does a warp drive enable a starship to go beyond the speed of light, and is this achievable for humans? So for you to be able to understand how a warp drive works, you need a little bit of background knowledge in one of the weirdest frameworks of physics, relativity. So I won't go into detail about the entire framework. I will just explain you the basic concepts which you would need to understand how a warp drive works. So there are two parts of relativity that you need to know. You have special relativity and general relativity, and they're both created by one of the most brilliant people in all of physics, Albert Einstein. So since I won't go into detail about special relativity, there's basically only one thing that you need to know about special relativity. It basically says that you can't go faster than the speed of light. This is because, according to Einstein, mass and energy are directly related. So, for example, when you are accelerating, you will get more speed, so in turn, your kinetic energy will rise. And because your kinetic energy rises, your mass rises as well. And if your mass rises, you'll need more force, more energy to accelerate. And even if you manage to get that energy and you increase your speed, you will increase your kinetic energy also, and in turn your mass will increase even further, and this will continue until you reach a point when you will need infinite amounts of energy to accelerate, and this is basically when you're approaching the speed of light. This is by far not everything about special relativity. You have also time dilation and the twin paradox. There are many other things I could talk about, but the really one important thing you need to know for now is that special relativity basically says that you can't accelerate beyond or to the point of the speed of light, which is a problem because most of the planets, most of the stars are millions of light years away. So even if we could accelerate to a velocity close to the speed of light, it would take us millions of years. So that's why we would need a warp drive, which enables us to go faster than the speed of light. So let's move on to general relativity. General relativity is harder to understand than special relativity because it's a little bit counterintuitive, because we've always considered space and time to be different separate entities. We've always considered space to be like three dimensions and time to be something completely else. And Einstein proposed in 1915, what if space and time are interwoven into one big continuum, a space-time continuum. So maybe you've heard of this concept if you were a big fan of science fiction. So the space-time continuum is basically the universe. It's what the universe consists of. But Einstein proposed another thing. What if we could bend? What if the space-time continuum is bendable? So let's see, like if you have a mass like the Earth and you place it on the space-time continuum, it will bend. It will cause a disturbance in the field. Um, so I'm gonna give you a pretty good analogy right now. Think of the universe as a big trampoline, and think of the Earth as a bowling ball. What will happen if you put the bowling ball in the middle of the trampoline? It will bend, and it will like create this giant sort of well inside the trampoline. And so what will happen if you have like this tiny ping pong ball and you will shoot it across the trampoline? It will be attracted to the bowling ball because it has a downward hill towards the center of the trampoline where the mass of the bowling ball is placed. So you can consider the space-time continuum to be pretty much the same. If you have the Earth and you place it on a continuum, it will bend to the space-time continuum. Everything around it will be basically pulled towards it. And this, according to Einstein, is what causes gravity. So the main thing you need to know about general relativity is that the space-time continuum is very bendable, and this can come in quite handy when we are creating our warp field. In 1996, Michael Alcubierre found a way in which it was, theoretically speaking, possible to make a warp drive. Alcubierre said that objects in space might be limited by the speed of light, but that's okay. So here it gets really theoretical, but he said that space itself might not be limited by the speed of light. So he said, what if you could bend the space-time continuum to basically make space move around you while you yourself are actually not moving at all? He said that this could be achieved by compressing the space in front of you and stretching the space behind you out, causing a sort of wave effect which would enable you to actually sort of surf across space. And since you and your spaceship are inside of a bubble in which the space is not stretched out or compressed, and since the space in front of your bubble is compressed, the normally spaced bubble won't have to travel as much distance as it would have. And this technique of warping the space-time continuum would actually enable you to achieve speeds well beyond the speed of light. So now that we know that a warp drive is physically, theoretically speaking, possible, is it also achievable for humans? So I'm gonna state the obvious right now. It's not achievable with our current technology. But not all hope is lost, because maybe in the future we will be able to. So now let's look at what we need, what developments we need to have before we will be able to develop a warp field. So one of the problems is the amounts of energy it would take to create a warp field. So sources say it could be anything from 1 million Hiroshima bombs up to the entire mass of Jupiter converted into pure energy. So where will we get that kind of amount of energy from? Well, in Star Trek, they use a matter-antimatter converter. So you might think that antimatter is something made up, something that belongs in the world of science fiction. But antimatter actually exists. So the idea behind antimatter is that for every normal particle, for example an electron, there exists an antiparticle, an anti-electron. An anti-electron is also called a positron. But so these antiparticles have exactly the same mass as the normal particles, and they are almost identical in every other physical aspect. But they differ in one aspect. Antiparticles have the opposite charge to uh, the normal particles. For example, as you might know, an electron is negatively charged. So a positron, an anti-electron, is positively charged. But the main thing antimatter is most known for is that when it comes into contact with normal matter, they annihilate each other, and with this annihilation, a huge amount of energy is released. And we could use this energy to power our warp drive, but there is a problem with antimatter. Not that we don't know how to create it, we know how to create it, but the problem is how to contain it. Since antimatter is so explosive, we need to contain it because otherwise it would be a danger. Because you don't want a million Hiroshima bombs to explode in your spaceship, because that would basically kill everyone on it. So one way to contain it is with a magnetic field, holding the particles in place and guiding them when their annihilation energy is needed. So using antiparticles is possible, but very dangerous due to their very explosive nature. So another big problem is that for stretching the space-time continuum in such a way, negative energy is needed. And negative energy might sound like something straight from a science fiction movie, but it's theoretically proven and experimentally proven that negative energy is actually real. So negative energy is present in a physical phenomena called the Casimir effect. I won't go into detail into this because we would have to discuss a lot of quantum field theory, and that would take way too long to explain in one video. So according to quantum field theory, you can never truly reach a zero energy. There will always be this little residual energy left in the vacuum, also called zero-point energy. So in this residual energy, fluctuations might arise. So this is actually called virtual particles, but for the sense of simplicity, I will call them energy fluctuations. So back to the Casimir effect. So imagine that you have two uncharged plates placed very closely together in a vacuum. And since they are placed so closely together, the quantum fluctuations are much smaller than outside the plates. So giving it, relatively speaking, a smaller energy than outside the plates. And since outside the plates is the zero-point energy, since it's a vacuum, the energy between the plates is, relatively speaking, a negative. So now that we know that negative energy is theoretically and experimentally possible, we only need to have the needs and the methods to harness this energy for our warp drive. So, but we don't have those methods yet. So a warp drive is still, although it's theoretically speaking possible, it's practically speaking still far away from becoming a reality. So maybe in the future we will be able to explore strange new worlds, to seek out new life and new civilization, to boldly go where no man has gone before. So thank you for watching this very first episode of The Science Of. I hope you enjoyed it. But could you maybe leave in the comments section, leave me some tips for my next video, or what went well and what I could do better so my videos will get better in the future. Well, anyway guys, I will see you in the next video.